steels for fast breeder reactor steam generator applications. So outline of the talk is we'll talk about power plants, then demand of high temperature materials for power plants, then introduction to high temperature deformation under loading condition, which is so called creep, then family of 9% chromium ferritic martensitic steels. Then we'll talk about effect of microstructural heterogeneity and welding processes effect on P91 steel weld joint, and effect of weld geometry, the geometry of weld joint preparations influence on type 4 cracking of joints, and also the addition of boron in the 9 chrome 1 moly steels, how it is going to behave in the high temperature environment. Then subsequently we'll talk about the next version of the grade 92 steel creep behavior. I will summarize. The first this is a typical diagram which shows the prototype fast breeder reactor, where the heat is generated at the core is taken up transferred through the radioactive coolant. This radioactive coolant transferred the heat to the non-radioactive sodium, liquid sodium, through intermediate heat exchanger, which goes to the steam generator. And from the steam, whatever the generated goes to the turbine, and the high pressure, intermediate, and low pressure turbine. Depending upon the temperature experienced from the core to the turbine, the material is being selected based on temperature, based on load, and also the environment seen in the by the component. And also this conventional, the 9 chrome family steel is also being extensively used in the conventional power plant. This is the major material for high temperature applications. Here in the x-axis, which has shown that the temperature which can withstand for longer duration, the materials, about 600 to 625 degrees centigrade, about 9 to 12 chrome family of steel, ferritic martensitic steels or ferritic steels, and above 650 to in the range of 650 to 675 degrees centigrade, the austenitic steels family is being used, and above 700 degrees centigrade, nickel based alloy is being used, depending on the temperature. So even though the operating component temperature is about 600 to 625 degrees centigrade, as a materials researcher, we also have the responsibility to increase the component life by developing the advanced materials, even the given operating temperature. So the further the talk of this, now we'll be talking about in the ferritic steels. So before going to the main talk, we'll discuss about how the high temperature deformation. This is the typical stress strain, tensile stress strain diagram, which is the stress is increases, the strain is increases up to beyond the maximum load, and the stress is decreases due to reduction in cross section and leads to fracture. If the component is kept at the particular load or stress at a given temperature, mostly above 0.4 into melting point in Kelvin, what's going to happen in the dimension of the component? So it's the machine which we can talk, which studies about the creep behavior. It's a single lever arm uniaxial creep machine, and through lever arm the load is applied, and it goes to the sample through the lever arm. It's the fulcrum, and the furnace which can give about 1000 degrees centigrade maximum, and the temperature is measured through K-type thermocouples, and temperature is being controlled through PID controllers. And deformation is measured the mechanical extensometer and attached with the digital indicator. So this is the typical creep curve looks. With the time there is a change in strain. The creep is defined as the time dependent plastic deformation of a material at a given temperature, at a given stress, at a given environment. The stress can be uniaxial, stress can be biaxial, stress can be triaxial, and this is the high temperature. And the environment, it can be the normal air environment or liquid metal environment, like for example the sodium, and gas environment, inert gases, where the advanced gas cooled reactors are the component that's seen by the inert gases. How for example helium cooled reactors, how the material is going to behave with in the presence of helium also been studied. So combinedly, it's the time dependent plastic deformation behavior of a material. So the creep curve, after initial the constant load, with the time the strain is being observed. In the initial stage, the rate of deformation is reduced, and further the rate of deformation is a constant, and after certain duration the rate of deformation is faster. So for our depending upon this phenomena, the creep curve has been uh, classified in the primary stage, secondary stage, and tertiary stage, where the primary stage, as we discussed, low deformation, and secondary stage are steady state deformation, and tertiary where accelerated deformation terminates at the fracture. So what are the informations we are getting from it? First, the main thing is how the dimensional change of the component with the time happening, and also the rate of deformation, and also the failure time also we will be getting the information by in these studies. So coming to the 9 chrome ferritic steel, ferritic martensitic steels, this is, since this steel we can call it also 9% chromium ferritic steel. This choice of material is selected because this material possesses better creep strength and the high thermal conductivity, which is most important property for steam generator is concerned. The high thermal conductivity and low thermal expansion coefficient and high stress corrosion cracking resistance. When the heat is transported from higher to lower, there will be if the thermal conductivity is less, there is a buildup in thermal stresses. So this material is selected because of it has the better properties towards the steam that thermal conductive applications. So main concern in this family of steel is when the component contains the weld joint possesses the lower creep strength under creep and creep fatigue interactions. So now let us see now how do we arrive the 9 to 12% chromium. If with increasing chromium, the strength is increased, the rupture time with chromium concentration is shown. The 9 to 12% the strength is maximum. Beyond that, beyond 9 to 12%, the strength is degrading because of presence of delta ferrite formation, which is softer than the martensite structure. So the major alloying elements added in these 9 chrome steels, the chromium basic alloying elements, which is added for corrosion and corrosion resistance and hardenability, and also to enhance the strength of this 9 chrome steel, 9 chrome and aluminum, 9 chrome and iron alloy. The molybdenum and tungsten and cobalt is added as a solid solution strengthener because the atomic radii is higher, which gives the lattice strain, leads to increase the solid solution strengthening. And also, in order to place the carbides along the boundaries, we added the carbide forming elements: vanadium, niobium, titanium, tantalum, carb. These elements combine with carbon and nitrogen forms the carbonitrate or carbides. So carbon and nitrogen is also a austenite former, which prevents the delta ferrite formation and also act as solid solution strengthening. And boron is added also in the steel to strengthen the boundaries to stabilize the precipitates or carbides. And silicon manganese added for oxidation and corrosion resistant purpose. And nickel is mainly an impurity in this alloy. And copper and cobalt is austenite former, is added to avoid delta ferrite formation. Copper, palladium is added as a fine nanoparticle precipitate forms. So this now the generation of 9 chrome steels in 1960 it started 9 chrome and 1 moly only. So this can be operated about 550 degrees centigrade. We can utilize this alloy for operating temperature of 550. About in late 80s, the addition of vanadium, niobium, and carbon nitrogen, which forms the fine about 20 to 30 nanometer fine precipitate forms in this steel, which gives the better high temperature strength. So the operating temperature also can be enhanced about 590 degrees centigrade. In late, about in 90s, the tungsten is added in this 9 chrome 1 moly steel. Tungsten provides as a solid solution strengthener, as we have seen, because higher atomic diameter, which gives the lattice strain. This is called grade 92 steel. Which gives about 15% higher strength, high temperature strength than the 91 steel, and also operating temperature can be increased at 620, around 615 degrees centigrade for a given period of time. For 1 lakh out, this temperature as mentioned for a given period of time, what stress it can withstand, constant stress, and this much temperature it can withstand it. So the further advanced materials also been enhanced for 650 degrees centigrade. We will discuss in later. So the 9 chrome, this 9 chrome ferritic steel family is normally being subjected to heat treatment. By heat treatment, we can alter the strength of this material because the advantage taken from the phase transformation behavior. This steel from room temperature, the BCT structure or ferrite structure to the austenite while heating, and while cooling it forms 100% ferrite, 100% martensite structure it forms. So which is very brittle structure. It is because the fine lath structure formation and because transformation induced high dislocation density. So martensite is the very hard brittle structure. So we also need to, after normalizing, we also need to temper. So to restore the ductility, to increase the ductility. So the dislocation density will come down, so the ductility can be enhanced. So now the 9 chrome 1 moly steel, which is invented in late 80s, and still the research is going on for the further improvement. The typically this steel passes, as we discussed earlier, various boundaries, grain boundaries, superior austenitic grain boundaries, packet boundaries, block boundaries, and lath boundaries. Various boundaries are decorated predominantly by chromium carbide precipitates, which is size about 80 nanometer, and inside the lath boundaries in the matrix, the MX precipitate, vanadium niobium carbonitrate precipitate, which is size about 30 to 40 nanometer, which is very fine size, is being decorated inside the lath structure. So in the right hand side bottommost picture, we can clearly see the lath structure decorated by chromium carbide precipitates and intra-lath structure MX precipitate. If the lath width is finer, the strength is more. If the precipitates are finer, the strength is more. Because the finer precipitates retains the dislocation structure for the longer time. So the benefit of dislocation strengthening also will be getting. In addition, this material also been solid solution strengthened and boundary strengthening. So this is the type of precipitate we have discussed earlier. What are the factors in order to keep the better creep resistance? The precipitates should not grow. It should be as fine as possible during even the service time. It should not get coarsened, and also the distribution should be uniform, and the coarsening of lath structure should be delayed. We cannot avoid it, we can minimize it, and dislocation density should be there to it should be retained in order to get the better creep strength. And subgrain formation, because of subgrain formation, by reducing the dislocation density should be avoided. This is a typical phase diagram which shows about the precipitates dissolution temperature and its stability. MX precipitates till about 1100 degrees centigrade, it is stable. Chromium carbide precipitates about 850 degrees centigrade, it's a stable. Lava phase about 650 degrees centigrade. That in order to get the better creep strength, as we discussed, at precipitate should be very finer, which gives the better precipitate strengthening, which retains the dislocation structure, which dislocations obtained either phase transformation or work hardening, and solid solution strengthening, which gives the creep strength in addition to the inherent creep strength of the matrix. This is the typical P91 steel microstructure. And when we do welding, so due to the heat source, depending on the peak temperature, the transformation, depending upon the peak temperature, the transformation occurs across the heat affected zone. From melting point to the 1100 degrees centigrade, whatever the precipitate we discussed, it was dissolved. Due to that, the grains become coarsening, the so coarse grain formation. The temperature between 1100 to 900 degrees centigrade, 900 or AC3 temperature, the MX precipitate doesn't dissolve because of more stability. Chromium carbide precipitate dissolves, and due to that presence of MX precipitate, fine grain size formation occurs in this temperature regime. The temperature between 900 to 820 degrees centigrade, AC3 to AC1 temperature, MX precipitate presence and chromium carbide precipitate partially dissolves. In addition, whatever the martensite structure in room temperature exists in the base metal, it partially transform to austenite. Certain region transform, certain region doesn't transform. So partial transformation occurs between AC3 to AC1 temperature, and below AC1 temperature is the over-tempered unaffected base material. So we can clearly seen here from weld metal to the base metal, the variation of within the short HAZ region, about typically 2 to 4 mm width of heat affected zone, which varies depending on the welding process. The weld metal microstructure, which is the dendritic core structure, then coarse grain region, which is about 40 micron period austenite size. The next is the fine grain region, which is about 14 micron. The next is AC3 to AC1, the temperature regime, which is the intercritical heat affected zone, which is about 8 micron, and the base metal is 20 micron. And for better creep properties, in order to get the better creep property, we need to have the coarser grain size, so the diffusivity can be reduced. If it's the finer grain size, boundaries are porous structure, the more diffusion happens, then all the element will come to the boundary, will lose the creep strength. So in order to get the better creep strength, we need to have the coarser grain size. So in addition to that, within the short dimensional, there is a heterogeneous grain size variation. As we know that this is going to influence the heterogeneous mechanical properties. In a period to that, we will also see what happens to the precipitate during welding, particularly in the heat affected zone. In the coarse grain, all precipitates dissolve. In the fine grain region, the right hand top image, all the precipitate MX retained, chromium carbide precipitate dissolved. Whereas in the case of intercritical region, where the temperature between 900 to 820 degrees centigrade, there is a partial transformation to austenite while heating, and while cooling, the fresh martensite forms. In the process, that precipitate also dissolved in certain regions. Certain regions precipitate partially dissolved. The precipitate, either it should completely dissolve or it should not dissolve. Here, what happens? It's a partially dissolved it. It's about 70 nanometer. What happens, since the precipitate exists, but the matrix transformed to austenite while heating, and while cooling, it fresh martensite forms. So in the process, we lost the precipitate strengthening. What happens here, we can closely see whatever the precipitate decorated along the boundaries were lost here because of transformation to austenite during heating. While it's cooling, the boundaries forming in different locations. So the precipitate are decorated along the boundaries, only we will be getting the more benefited rather than the other locations. So after the welding, the post-weld heat treatment in the intercritical region, the precipitates further coarsened about around 140 nanometer, from the about 100 nanometer to 140 nanometer. We are losing the precipitate strengthening in the material during the welding process itself, period to the service. So also we can clearly see that the most of the precipitate inside the boundary. So we are losing the boundary strengthening also because of precipitate moving away. So we'll see also when at the high temperature applications and during service or under creep, how it is going to precipitates gets coarsened. So basically we can come to the one point here. The damaging region during the welding is the intercritical heat affected zone, which is coarser, which has coarser precipitates, the boundaries divide of precipitates, and very fine grain structure. And also in the intercritical region, the boundaries are high angle boundaries. The low angle boundaries are the slow diffusion process, allowing the slow diffusion, and high angle boundaries fast diffusion occur, leads to more damage, whereas in the intercritical region also has more high angle boundaries during the welding process it generated. And here the microstructure further classified, the yellow color, the substructure, the retained, whatever the base metal structure, it's retained. The blue color, which says during welding, it got recovered, it got softened. When in the red color deformed structure, which is between the precipitate and the matrix interface strain is there. So if you see at the weld joint, weld metal, coarse grain, fine grain, and the base metal, the substructure still exists, and the heterogeneity within the intercritical region, the differences between recovered structure and substructure and deformed structure is more. So what the study says is that the heterogeneity exists across from weld metal to the base metal, and also the within the intercritical region there is a heterogeneity exists. So this how it's going to affect our creep behavior. This is the variation of hardness across the weld joint from weld metal to the base metal in the as welded conditions. Once it's further post weld heat treated, in the intercritical regions it gets softening more, because obviously already the precipitates were coarser during welding, and further coarsening during post weld heat treatment, and also dislocation density is reduced. Due to that it's a lower hardness is being observed in the intercritical region as compared to other regions. And moreover, for better creep strength, the heterogeneity, even though weld joint having the different microstructure, the material property should be either high to low or low to high. There should not be the heterogeneity between them. So that's why we can clearly see here the weld metal is a more hardness, and base metal through HIZ there is a dip in the intercritical region. Again, there is an increase in the hardness in the base metal. And each zone tensile properties, how it is changed. The base metal, coarse grain, fine grain regions, more or less the tensile strengths are comparable. And in the intercritical region, there is a drastic reduction in tensile strength. Coming to the deformation, it's a localized creep deformation study, which is called impression creep. In each weld metal, coarse grain, fine grain, intercritical region, and base metal, locally how at a given constant load and given temperature, how the deformation occurring is being observed with the time. It is very significant to note that the intercritical region deforms faster than the other regions at a given time. So this also confirms that the intercritical region is a softer region. In addition, across the weld joint, there is a heterogeneity in deformation behavior. So how this leads to the component which has the weld joint, the specimen which has the weld joint has failed very early, prematurely, as compared to the base metal, which has seen about 7,000 hours. The weld joint has seen only 1,000 hours. So which is very drastic reduction in the power plant component. When we design based on the base metal data, under given service conditions, this weld joint, if it is there in the component, about 30 to 50% reduction in the creep strength happens because of due to microstructural damage because of welding processes. So they basically, depending upon the cracking location, the cracking has been classified. If the crack occurs during service in the weld metal, within the weld metal cracks remains, it is type 1 cracking. If the crack occurs from weld metal to HIZ, across the HIZ to weld metal, which is type 2 cracking. If the crack or failure occurs very close to the weld metal, which is coarse grain area, which is type 3 cracking. And if the cracking occurs in the intercritical region, which is a type 4 cracking. So type 4 cracking is mainly occurs in the localized deformation and localized cavitation damage. Also, this process, this premature failure also varies depending upon the welding process. If we apply the single pass welding process, electron beam welding, and the activated TIG welding process, the creep strength can be enhanced by the single pass welding process than the multiple passes welding process, which is TIG welding SMW. We can enhance the creep strength about 15 to 20% if we apply the single pass welding process as compared to multiple welding process. It's the weld strength factor, which dictates about weld strength factor, which says that single pass welding process provides a better creep strength than the multiple process. So the microstructure heterogeneity and the welding process influence. If we change the thickness, will it going to affect the creep strength or not? So we have changed the different, keeping the parameter constant, the specimen thickness changed. It's very significant to note that the change in specimen thickness, the rupture life is significantly varying. So very thin sample and very thick sample, it's shown very lower life, and the 10 mm thickness, it's shown the better creep strength. So but however, all the samples has failed in the type 4 cracking. Here we measured the strain, localized strain at the fracture location, and thin sample has shown the more strain, and thick on 10 mm sample has not shown significant strain. Whereas the creep damage, cavitation damage, as we discussed, it's a localized creep damage and a localized creep cavitation and deformation. So cavitation we measured at the intercritical region and different depth level. It is significant to note that at thick samples, there is a cavity is more predominant, whereas thin sample, it has mostly failed by deformation than the cavity damage, which has been shown here. Localized deformation occurs at the intercritical. And also here we can clearly see that thick sample has failed by cavity damage, creep cavitation, thin sample by plastic deformation. So if we change the groove angle, will it going to change the creep behavior? We changed the groove angle, the 90-degree, which is single pass, and 35-degree bevel angle, and 45-degree and 60-degree. It's significant to note that the change in groove angle, the rupture life is changes. If the lower angles, which is about square butt joint and 35-degree bevel angle, provides the better creep strength than the more higher groove angle joint, because the higher groove angle joint we use the multiple thermal cycles needed to deposit the material. So which are multiple thermal cycle also leads to damage the base metal microstructure, resulted in lower creep strength, which we can see it here. The damages in the heat affected zone, type 4 cracking, all the samples, and creep cavitation damage. So the preferably, if possible, square butt joint or 35-degree groove bevel angle is suggested to better component life. So type 4 cracking is the influence of not only the microstructural damage during welding, and also welding process and the thickness and groove angle. So if we add the boron in the steel, will it able to benefit us for a better creep strength? If we add boron, so it should be in as a free element, boron in the material. It should not form as a boron nitride. So we need to adjust the alloying, control the nitrogen, so that free boron is available in the material. So we need to adjust accordingly. So we added a boron about 50 ppm and nitrogen controlled about 100 ppm. Generally in the T91 steel, about 700 ppm nitrogen will be there. We reduced it to 100 ppm and added 50 ppm boron, and found that the precipitates are very fine in normalized tempered condition, and lath width also very finer, leads to high temperature tensile strength in this addition of boron. So addition of boron also leads to, here the creep rate versus time curve is shown here. The black curve shows that the steel without boron, and the colored line shows the steel with boron. The deformation rate is very fast in the steel without boron. With boron addition, about 2 order of deformation rate is minimized. And coming to this graph on the applied stress versus rupture time, the 3 different temperature is shown here. At a given time, at 550 degrees centigrade, about 60 MPa strength can be, creep strength can be enhanced. And at 600 degrees centigrade, 40 MPa can be enhanced. At 650 high temperature, about 30 MPa strength can be enhanced at a given time, about 10,000 hours. So it says that addition of boron leads to improve the strength significantly. So we can fabricate the component by boron added grade 91 steel, which also the enhanced, because the right hand side, the picture which shows that the steel without boron, which has seen only 500 hours under similar testing condition, the boron added steel has shown 27,000 hours, whereas the precipitate sides, we compare it about 180 nanometer, even 27,000 hours, it retains the precipitate stability, which gives the better component life. The weld joint also provides the better creep strength of weld joint boron added conditions as compared to the steel weld joint as without boron, because of microstructural stability. So the next is we discussed the tungsten as a solid solution strengthening. So how it is going to, we added about 1.5 tungsten weight percent, and molybdenum reduced to 0.5% in order to avoid delta ferrite formation. So it provides about 15 MPa strength higher than the grade 91 steel for 1 lakh hour lifetime. But the main concern is whatever we added the tungsten, it comes out as a lavas phase formation, which is the main concern. Or otherwise, it is the best material as compared to grade 91 steel. This weld joint also we studied, and this also typically failed in the type 4 cracking and in a brittle manner and localized creep cavitation. If you look at this graph, the grade 91 base material, green line, and blue color is the weld joint. There is a drastic reduction in the life of the weld joint as compared to base metal grade 91 steel. If you look at the grade 92 steel, also the reduction in creep strength occurs the joint in the weld joint. The reduction is relatively less as compared to the grade 91 steel. So the grade 92 steel is being used and also being considered heavy sections in the conventional power plant, and also we can utilize this material for steam generator applications because the microstructural stability is better. And if we combine the boron, benefit of boron and benefit of tungsten, we can better develop the new material. So if we increase the tungsten about 3%, if we increase the tungsten 3%, there is a delta ferrite formation. If we add a cobalt as austenite stabilizer, so delta ferrite can be minimized. So 3 tungsten, 3%, 8% cobalt added, and also boron added along the 9 chrome steel. So 9 chromium, 3 tungsten, 3 cobalt, and boron added with nitrogen controlled will develop the 650 degrees centigrade, the significant improvement in the creep strength compared to grade 91 and boron added 91 steel and 92 steel, which shown here. The bottom, the graph shows about 92 steel, and the top graph shows that 9 chrome, 3 tungsten, 3 cobalt, vanadium, niobium, boron added with controlled nitrogen, about 130 ppm boron and 50 ppm nitrogen, which shows about till about 10,000, 20,000 hours, the weld joint still not shown any type 4 cracking indications, which can clearly shown in the graph. The weld joint is following the trend of base material. This material being used in research laboratory and also being considered the advanced material, this material will be used in the conventional as well as nuclear power plant in the forthcoming years. To summarize this talk, the basically 9 chrome 1 moly steel, 9 chrome family steel, when we develop the base material for 1 lakh hours, this much strength should be there, operating temperature has to be this much. We need to consider during welding how the microstructural degradation happens across the HIZ, how and within the intercritical region, how we are going to minimize the heterogeneity from weld metal to the base material and within the intercritical region. And also the geometry also plays the major role in addition to the composition development for the component which is the high temperature. And thank you very much for giving me an opportunity to deliver this talk. Any question, please? No response.
No question. I will conclude this first talk. Then we will invite in the second speaker. Thank you, Saktivel sir.
Thank you
for honoring as well as a love of KALPAKKAM IEI KLC token of love. We will give one small memento to speaker right now, and we will move on to the next speaker. Please. Thank you, Saktivel. I call upon the next speaker, G. Ramanathan. வெளியில போயிட்டு வரணுமா? வெளியில போயிட்டு வரணும். வெளியில போயிட்டு வரணும்.
sir.
Am I audible? Good evening, sir.
Yes.
Am I audible, sir?
Yes, audible. Thank you. Start, sir.
Yes, sir. Thank you, sir. A very good evening to all of you. I thank the Institution of Engineers Kalpakkam Local Center for giving me this opportunity to talk this presentation in front of you. First, let me introduce myself. I am G. Ramanathan. I belong to electrical engineering, and my field of working is the operations of electrical substations. I am working in engineering services group of Indira Gandhi Center for Atomic Research, popularly known as IGCAR in Kalpakkam. This small introduction about this IGCAR is for the audience who do not belong to Kalpakkam. IGCAR, Indira Gandhi Center for Atomic Research, is an second largest establishment of Department of Atomic Energy of Government of India, next to the BRC Mumbai, which is located in Kalpakkam, which is 80 kilometers south of Chennai and 20 kilometers south of Mamallapuram. IGCAR has been established to conduct a broad-based multidisciplinary R&D activities towards the development of fast breeder reactor technology and its associated R&D activities. As a this FBR technology is the second stage of Indian nuclear power program, which is based on the plutonium-based reactors of sodium-cooled type. As a part of this development of FBR technology, a sodium-cooled fast breeder test reactor has been established in IGCAR, and so many related R&D activities are also carried out in IGCAR. Apart from the IGCAR, some R&D facilities of BRC and some plants of BRC also are located in Kalpakkam. In addition to this, popularly known Madras Atomic Power Station, MAPS, also is located in Kalpakkam. With this, I'm moving into the topic. I'm not going to touch the detailed technical aspect of this project. I'm aware that the audience are comprising of engineers of various disciplines, but for today's session, I have selected a topic from electrical engineering, but I'm sure that it will be an interest for electrical engineers who have not dealt with EHV systems, 230 kV transformers, and for the others, it will be a window for knowing what electrical engineers are doing. With this small introduction, I'm going into this topic. For reliable R&D activities of BTR and associate R&D laboratories located in IGCAR, we need a reliable, quality, uninterrupted power supply for doing the research in proper manner and to get the desired results. For that, for providing power for this R&D activities and for providing offsite power supply to a BTR, 33 kV CSS was established in IGCAR. It is getting power supply from MAPS. MAPS is a atomic power station located in Kalpakkam, which is having two generators of 235 megawatt capacity, and they are feeding power to southern grid through 4 numbers of 230 kV power lines, and also provided power to the IGCAR at 33 kV level by stepping down the 230 kV power supply to 33 kV by stepping down transformers located in MAPS switchyard. Actually, two methods of power supply arrangements are used in nuclear systems. One is that 1 out of 2 configuration, that is 2 units of 100% capacity, and 2 out of 3 configuration, which is 3 units of 50% capacity. This is the power supply arrangement and single line diagram of IGCAR power supply arrangement. Here, the original arrangement before 4 decades ago, this CSS 33 kV CSS in IGCAR which was receiving power supply from MAPS directly through one feeder, and the second feeder also was availed from MAPS directly to 33 kV CSS, and power is fed to a BTR by two numbers of 33 kV feeders. Say this is a BTR1 and a BTR2 for providing offsite power supply to a BTR, and to other laboratories and BRC facilities and two townships in KALPAKKAM by through two numbers of 20 MA transformers in CSS. But later on, based on the load growth development in KALPAKKAM of various DA units, one more one more source was added into the system. That is one 50 MA transformer of 230 kV by 33 kV by 11 kV into the system, and one more 20 MA transformer was added into the system. This is the development of 33 kV CSS in IGCAR. The source side of this system, that is MAPS areas components such as transformers, circuit breakers, the cables from MAPS to IGCAR, all were four decades ago, which needed refurbishment in line with the latest technology, such as that electromechanical relays, which have to be replaced with the numerical relays, and MOCV panel boards to be replaced with the VCB, PIL cables to be replaced with the XLP cables. Like that, so many activities were planned for refurbishment. During this time in 2012, one of the source transformer, that is IGCAR transformer 2, 25 MA transformer 2 at MAPS, which got failed due to the bushing failure. So it was decided to commission the feeder with the new transformer of enhanced capacity and take up this refurbishment work also in addition to this transformer enhancement work. The failed transformer, that is 25 MA transformer 2 in MAPS, which was having only one secondary winding to feed IGCAR loads. That means 33 kV for IGCAR. During this replacement period of this transformer, post Fukushima retrofit, that was being executed at MAPS, and a lot of improvement works were done. Let me brief the Fukushima effect and its post retrofitting activities in brief. In 2011, March 11, an earthquake of 9 Richter scale and followed by 15 meter tsunami that affected the Japan coastal area. In that area, that Fukushima nuclear power plant was there, which is also getting affected. There was a power plant of 9,000 megawatt capacity of 11 reactors. In that power plant, some reactors were in operation and some reactors were in shutdown condition. The reactors which were in operation, they went to shutdown mode during the earthquake automatically. But due to the tsunami floods affected the nuclear power plants, the power supply to cooling pumps for RHR, that means residual heat removal from the reactor, they got failed. That means the cooling pumps lost power supply, and which affected in the melting down of the fuel rods. So there was a reaction of metal and water took place in that reactor, which resulted in the hydrogen gases. So due to this, radioactivity has happened in around the nuclear power plant of 20 to 30 kilometer, and which created some evacuation of 1 lakh people from that area. So this safety problem, then this flooding condition was reviewed and evaluated by various international national safety committees, and so many improvements activities were recommended and that were adopted in all over nuclear power plants in India. Some of the improvements activities carried out in MAPS KALPAKKAM, that were some adding up on exclusive 200 kVA air-cooled DG was introduced at 5th floor to meet this flooding conditions, and which is to feed power supply for fire water pumps and emergency core cooling systems and other control supply units. And the battery capacity was also doubled. That control room was completely powered up with solar power with 3 days backup. And important parameters, critical parameters were recorded by the meters that were converted as self-powered meters. So like that, so many activities were planned and executed in maps. So in addition to these activities, as an alternating source to off power supply to feed safety related loads of maps. So parallelly, IGCAR transformer enhancing augmentation work also was planned. So put together, it was planned to decide to install a new transformer and switchgear at an elevated platform, that is plus 13.2 meter from MSL. The existing transformer, which was located in plus 11.6 meter from MSL. So 1.6 meter cushion is obtained. So this one at this higher elevated platform to be built, and over this switchgear and transformers to be installed to safeguard any flooding condition. So the following modifications were there as compared to the old system. So means that new transformer, old transformer is 47 MVA, now the new transformer is 47 MVA with 2 secondary windings. One is 35 MVA at 33 kV level for IGCAR and 12 MVA at 6.6 kV level for maps. The second one is the transformer which is to be installed at the outdoor on the elevated platform of 1.6 meter height. The 230 kV lines which is available at the inside transformer bay, which has to be brought out, that is another modification. Third one is the switchgear and lightning arrestor and other equipments to be installed over a elevated platform, that is to make the existing transformer bay with Fukushima compliant 230 kV bay. This is the modifications were planned. The figure shows the transformer bay after the removal of the old failure transformer, which was taken out from this transformer bay to outside. This is the place where we have planned for installing this new transformer with in a higher elevated platform. This is the 230 kV bay which is feeding power supply to Bhavini, that is PFBR construction. So in this project, the following major challenges we identified. That is the first major challenge what we identified is the shifting and installation of wall bushings, each weighing 1.7 tons, 6.8 meter length with the center support plate and to be matched with the wall EPs at 9 meter height. This is the main thing, that installation of bushings at 9 meter is the major challenge, because we have to install the bushings at this height. Actually, wall bushing, this is the general drawing of an wall bushing. This is an insulator which allows a passage of conductor from one portion to another portion through a conducting barrier. This is the wall bushing. This is a conducting portion, wall supporting plate. This is the CTs, wall bushing CTs. So this portion is connected to the indoor switchyard of maps to tap the power supply, and this portion is connected to the transformer terminals. So that the conductor has to pass through the conducting portion of the wall, so supporting plate. So this is a conducting portion. So through this, it has to be taken out. This is the general drawing of wall bushing. This is CT. The second challenge what we have identified, this shifting and installation of surging arresters, HV switchgears, protection panels, and NGR at an elevated platform in a restricted space to meet the beyond design basis flood level. As we have seen, this is the small area which was available for us to build the bay and to be converted as Fukushima compliant switchgear bay. This is a second. In this area, we have to build the platform over and above the equipments, everything we have to build. This is the one challenge. Another challenge we have identified. The third one is the execution of entire project in the close vicinity of live 230 kV lines with proper safety precautions, because this adjacent bay is a 230 kV live bay. In with the proximity of this live condition of this bay, and we have to execute the entire project. That is the one challenge we identified. The fourth one is this integration of control and relay scheme with the systems of an operating reactor with the multi-level approval at each stage. Actually, one major change in this scheme, what we done is this that we'll explain. I will explain the subsequent slides in the transformer change. The CTs, transformer protection CTs, were located inside the transformer bushings in the old transformer. The failure reason for the old transformer was mainly due to the flashover occurred in the CT turret of the old transformer bushing. So it is decided to take out the transformer protection CTs from the transformer bushings to wall bushings, so that any problem or any flashover occurs in the wall bushing that will not affect the transformer. So that is a major change we have done in this new wall bushing. So CTs are shifted here. The second one, so because of CTs shifted here, the CT sizing is mainly depending upon the knee point voltage of the CT, and that is affecting the weight of the CT. So to minimize the weight and to make this system simple and easy to install at higher elevation, we have to restrict the knee point voltage of the CTs. To minimize the knee point voltage of the CTs, that lead resistance to be minimized. So in the previous old scheme, this is the control relay panel located in mezzanine floor of MAPS. The old system, we can see this control panel and relay panel, they were in the adjacent to each other. And this new scheme, because to reduce the knee point voltage, the relay panel is removed from this mezzanine floor and kept in the switchgear panel itself, which reduces the knee point voltage of the CTs to great extent. Now that means the entire system we had completely changed, and this is to be integrated with the existing system of the operating reactor. So we have meticulous planning and approval at each stage. That is one major, another challenge. And commissioning of this upgraded system without any incident and without any disturbance to the operating power system. These are all the challenges we identified. And the actions to overcome these challenges. The first one is the 3D bay modeling approach that we made for retrofitting the old transformer bay to accommodate HV panels, LES, wall bushings, and transformer. So this is the 3D bay modeling approach we made. So in which the 3D modeling was created so that the location of the each equipment, this is the transformer, this is the radiator, here that switchgear panel, here lightning arrestor, wall bushing, all these equipment layouts and location of the various equipments, all these things we have created. So which helped a lot to pinpoint the layout preparation. So based on this, and optimized layout design was made for locating outdoor transformer on an elevated platform, bus post insulator, outdoor lightning arrestor, and other electrical equipments. So based on the bay modeling, this is the layout we have prepared. So here, this is the location for 33 kV panel. This is NGR panel. This is 6.6 kV panel. This is protection panel. Here, transformer. This is inside wall bushing, lightning arrestor, outside wall bushing, radiators, cooler control. Like that, we made the complete equipment layout. And met all statutory electrical clearances for a 230 kV system in a high constraints place. Actually, 2.5 meter minimum clearance is required for 230 kV system as per MAPS guidelines, and 5 meter working clearance is required for carrying out any work in this 230 kV bay area. That we have met at each and every stage to meet these safety clearances. And meticulous planning, multiple mock-up drill sequencing, all helped us to overcome these challenges. And the activities carried out in chronological order. Actually, we cannot install or plan the works in a random manner. A sequential manner only it has to be executed. The first, the preparation of technical specification of all equipments, then procurement activities. Parallelly, we initiated the civil engineering activities such as the construction of elevated platform for transformer and switchgears, and the structural modification to house the wall bushings, and tendering and execution of for installing, testing, and commissioning the system. This one, the execution of works, removal of existing 230 kV indoor wall bushings and installation of new wall bushings, installation and testing of switchgears, protection panel, and other equipments, installation and testing of transformer and its accessories, power and control cabling, testing of various protection and control schemes, integration with the existing system. That the removal of existing 230 kV wall bushing, the existing 230 kV wall bushings we could not be able to use because that bushings were not provided with the CTs. CTs we have introduced in the wall bushing, so that old bushings have to be removed out and new bushings have to be installed. This is the photo which shows the site during the construction. Here, this is the elevated platform of 1.6 meter height. Over and above this only transformer will come. This is the platform for radiators. This is the civil structural modification done in the old transformer bed for taking out the outside wall bushings. This is the inside view of a 230 kV switchyard in maps. This is the wall bushing which is to be removed. This person is now removing the connection between the 230 kV bus bar with this wall bushing, which is at 9 meter, approximately 9 meter elevation. Here, what we done in this bushing, the existing fixing fastener templates we have made before approving the drawings for new bushings, and we exactly transfer this bushing fixing holes to the new bushings, so that without any deviation in the wall EPs, exact perfect alignment we could be able to get in the new bushings also. This is the arrangement for removing the old bushing, and in the same way only new bushings are also were installed. What we are seeing is this wooden platform is made at 9 meter height with proper scaffolding supports, and these bushings are loaded in the I-beams which are available at the top of the transformer bay, which that supports by proper chain block pulleys. These bushings were loaded and taken away. This is the photo which shows the bushings are taken out from that inside transformer bay. Some more photos during the removal and installation. This is a new bushing. The same way the old bushings were taken out and they were lifted and inserted into that portion. Some rail type arrangement we made in that one, that the old bushing and new bushings are taken out from old bay and bringing into that same bay. This is the arrangement. Now the old bushings are removed and this is the new bushings after the installation. The bushings are installed for inside bushings, and outside bushings also installed, and they are connected with ACSR conductors. This is the view of external bushings after the installation. During the installation of this bushing, one more problem we face. Actually, during this process of construction, procurement of this wall bushing, parallelly civil activities are also taken up, and they have civil people constructed the platform to 1.6 meters. So within the small space, we could not able to get space for taking the crane inside and lifting the bushings. So what we have done is separate a special 25-ton capacity crane was taken, and which has lifted this bushing from some 30-40 meters away from this place, and which has lifted and installed. Even though the weight of the bushing is around 1.7 ton, we have used 25-ton crane because of the higher boom length what we required. Because of that, this one challenge we faced and overcome. And this is the drawing which shows the power and control cabling are going in the this transformer. After the installation of transformer and radiators and cooler control cubicle, the photo shows like this. This is the single line diagram of the new transformer. Here, a single line diagram is a representation of electrical system in a single line. So it is a 3-winding transformer, 230 kV primary and 2 secondary windings of LV1 and LV2. The LV1 winding, that is 33 kV winding, is connected to IGCAR through 33 kV switchgear, and this 6.6 kV is connected to maps through 6.6 kV switchgear panel. This 230 kV is connected to bus B of 230 kV switchyard inside maps. Maps 230 kV switchyard is consisting of three 230 kV buses. One is bus B and another bus C, which are the main buses. They are connected with a bus coupler, and these are all these two buses are connected to maps generator 2, and this is connected to maps generator 1. This is a third bus, which is called a transfer bus, which is used to extend the power supply to any feeder in case a circuit breaker is out of service due to maintenance or any outage. So this conductor is connected to this bus B through this disconnecting switches, and the CTs are represented here and they are connected to the relays. And similarly for LV side also, the CTs are connected to the respective relays. This is the SLD arrangement. Now, that compared to old transformer, in this new transformer, certain modifications and additional features are adopted in line with this latest technology and new requirements. The first one is that capacity is increased. That is 25 MVA is increased to 47 MVA. That voltage ratio, the old one was 230 kV by 33 kV. Now it is 230 kV by 33 kV by 6.6 kV. The two-winding transformer is now three-winding transformer. The vector group of the old transformer was YN0D. Now it is YN0. That is, vector group is the, as we know, this is for non-electrical audience. Vector group is the vector relationship of the primary and secondary parameters of a transformer. Generally, this 0 means there is no phase displacement between the primary and secondary windings parameters. That means the group 1. Generally, for another change in this transformer is that provision of tertiary winding. That old transformer, there was a tertiary winding which is denoted by this letter D. Generally, that tertiary winding is provided in star-star transformer for providing path for the circulation of zero sequence currents. Actually, zero sequence currents are there because of the nonlinear portion operation of the magnetic material of transformers. Because that flux density is more to maintain the flux, because we know flux phi is equal to Bm into A. To maintain that flux constant and to minimize the area of the core, flux density is kept at a higher level, and the transformer is operated in the knee region of the magnetic characteristics. But in this case, we have removed the delta winding as per the recommendation of CBFP, Central Board of Irrigation Power, and the major manufacturers of transformer. What they recommended that up to 100 MVA capacity, tertiary winding is not required, because the failure of the transformers are mainly due to the presence of the failure of tertiary winding. But the problem of zero sequence currents we overcome by increasing the area and reducing the operating flux density to 1.73 Tesla rather than 1.9 Tesla. The another one is that oil type. The old transformers, paraffinic oil was used. The new transformer, naphthenic oil is used, which is having a high oxidation stability. So sludge formation and other consequences are reduced in this by using this naphthenic oil. The next one is the core earthing. The old transformer, the core earth is earthed inside the tank itself. But in this case, the core earthing is done outside the transformer tank through a wall bushing, so that the healthiness of the core can be checked at any time without opening the top cover of the transformer. That pressure relieving device in the old transformer was the explosion vent, which is provided over the top of the tank. It is having a diaphragm which will puncture and release the pressure in case of any abnormal pressure occurring inside the transformer, which is now changed with two PRD. PRD is pressure relieving device, which is provided on the two places on transformer tank, so which will release the pressure and immediately it will shut off, so that the exposure of the rest of the oil inside the tank to the atmospheric air is avoided, so that moisture entry and other problems are getting avoided. And one more thing, once it is operating, it will trip the both HV and LV breakers of transformers, and complete isolation is obtained. And one more point is that it is provided with down pipes. The old case explosion when diaphragm is punctured and oil is spilled out, there is a chance of fire and person may get injured around the transformer. So in this case, that pressure is getting relieved and the spilled off oil is brought down to the downside of transformer, so that fire risk and operator safety is increased. Buchholz relay is a gas operated relay which is used to protect the transformer at incipient stage itself. Earlier, old transformer, one relay was provided. Now it is two relays are provided as a redundancy and one relay exclusively for OLTC. One more protective device is SPR. This is sudden pressure relay, which is operating on the principle of rate of rising the oil pressure. This PRD is operating on the dynamic pressure. This is this static pressure increasing. This is operating on the rate of rise of pressure increasing in oil. That means it will initiate the trip signal within 10 millisecond for 40 psi per second pressure rise in the transformer, so that they protect the transformer at an earlier time when a serious fault occurs inside the transformer and the oil surges happen. Another improvement in this transformer is fiber optic based hotspot temperature measurement besides the conventional OTA and WTA. Conventional OTA, WTA were provided in old transformer for measuring oil temperature and WTA winding temperature. In addition to this, a fiber-based hotspot temperature measurement. That means a fluoro-optic technology is adopted in this temperature measurement. One fluorescence material which is embedded in the hotspot measurement area, and it is connected to one end of one fiber, and that fiber is connected to the measuring instrument. There one lightning impulse is sent through this fiber, and the decay time is mainly depending upon the temperature variation in that particular space where we have to measure the temperature. So according to that temperature change, the decay time is changed. Accordingly, that temperature is measured. Once temperature is measured, so many data analysis can be made by what temperature, what is the load and what winding temperature, what is the load and what is the oil temperature, and what rate it is increasing. So like that, so many analysis can be made. So another one is that conservator. The conventional type conservator is now changed with the atmospheric airbag conservator. That conventional type conservator is provided with 2/3 of oil and 1/3 of empty space for breathing action, expansion and contraction of transformer oil during its service. During this breathing action, the oil is directly exposed to air. Of course, it is provided with silica gel breathers, but still it is over a period of time, there is an entry of moisture in the oil and oil is getting deteriorated. But in this atmospheric airbag, the oil exposure to air is completely avoided because the air is not at all touching with the oil. Only air is atmospheric airbag only is expanding and shrinking so during the breathing action. So the oil contamination rate is drastically reduced. And one more arrangement is old one is 100% cooling arrangement. Now it is provided with 2 into 75% cooling arrangement for better cooling arrangement to minimize the thermal aging of transformer. And thermosiphon filter, which is provided in transformer, which is making online reclaiming process. That means the acidity in the oil is getting neutralized when transformer is in oil, transformer is in service itself, which provision were not available in old one. The another one is online DGA device. DGA is dissolved gas analysis, which is an effective tool to make the alarming signals for transformers when any problems or faults which is occurring in the developing stage. So when oil is exposed to heat and partial discharge and severe faults, they are getting decomposed and gases are released. The release of gas and the rate of rise of gas are mainly depending upon the severity of fault and the seat of fault. So DGA is an effective tool to detect the gases and concentration of gases so that very advanced alarming signals can be given and corresponding maintenance programs can be planned. So, but in older transformer, the DGA has to be done for every 6 months or 1 year, depending upon the maintenance schedule of the transformer. Sample has to be taken, it is to be sent to the laboratories, and values to be obtained, accordingly action to be taken. But in this online DGA device, it is provided in the transformer itself, and which is making and which is doing the online DGA in transformer in service for every 4 hours, and data are available for up to 2 years. The data are available. Concentration of different gases, that key gases of DGA, like ethane, methane, ethylene, acetylene, nitrogen, oxygen, hydrogen, carbon dioxide, carbon monoxide. So like that, gases are detected from the dissolved in oil by gas chromatographic method. Entire arrangement is provided in the device itself, and which is connected to the transformer, and the process is taking place in the transformer in service. This is one major new development adopted in this transformer. And location of CTs that we have already seen. Earlier transformer, it was inside transformer, it is outside. Then impact recorder. That transformer, while it is shifted from factory to site, there is one impact recorder is provided, so that we can ensure that the transformer has come without any abnormal impact during transportation. And vibration preventer is provided at the bottom of transformer to minimize the vibrations and noise level. And there is one ribbon provided for DP sampling. Degree of polymerization is the degree which shows the healthiness of paper insulation. So for taking that DP test, provision is made in the transformer tank itself. And one more device, online bushing monitoring device, which is to monitor and give the alarm signals of the monitor the vital parameters of bushing, like tan delta and capacitance. These two are the main parameters whose values to be monitored continuously, and proper action to be taken when they are exceeding more than the specified limit. So this is the some information about transformer. This is some information about wall bushings. That is rated voltage 245 kV, rated current is 1200 ampere, 1 minute power frequency voltage 506 kV, impulse 1050 kV peak, short time current rating 40 kiloamps per 1 second. This we are arrived by the fault current of 230 kV system. The minimum nominal creepage distance 7720 mm, that is 31 mm per kV we have taken, considering the saline atmosphere in the KALPAKKAM. And the weight of bushing we have seen 1700 kg, and rated dynamic current is 100 kiloampere. And the standard follows IS 209 IEC 60137. And some details of 33 kV and 6.6 kV switch gears, 36 kV, 1250 ampere, 70 kV, that is 1 minute power frequency voltage, LI voltage, lightning impulse voltage, 170 kV peak. Short time current rating is 31.5 kiloampere per 3 seconds. Rated dynamic current 80 kiloampere. There's some safety features we have what we have adapted in these switchboards are they are complying to the requirements of IEC 6227 and 200 to increase the operating safety. Actually, this is an internal arc classification, internal arc classified panel. Means any arc or flashover occurs inside the panel, it is safe to access the panel from all sides of the panel, and this is able to withstand the internal arc for 0.1 second. So to discharge the hot gases developed during the arc, there is a pressure discharge flaps are provided over the panel to provide the passage for hot gases during arc. And the rear door limit switch and logic and solenoid logics are provided, so that without switching off the breaker, the rear doors cannot be opened. And inbuilt earth switch and interlocked with upstream CB is also introduced in this panel, so that the earth switch can be closed inside the panel itself. In addition to this, conventional interlocks like separate shutters for bus side and the cable side bushings, which close automatically while CB is in run out, CB operating interlocks, etc. This is the internal view of 33 kV panel. Here the XLPE cables are made with the N terminations and ready to connect with the bus bars. This is the rear side view of panel. This is the front view of 33 kV panel. Here, this is the VCB chamber, this is PT chamber, so this is the auxiliary relay chambers, etc. And this is the safety shutters for bus bars and cables, which will be opening automatically when CB is racked in, and which will close automatically when CB is racked out. This is the operating handle for H switch, which is operated from the panel itself. The switch is located on the rear side of this panel. That means it is connected to the cable. So without opening the cable chamber, the H switch can be closed, and it is interlocked with the upstream CB. When upstream CB is in off condition, then only this switch can be closed. This is the rear view of a circuit breaker, vacuum circuit breaker, 33 kV vacuum circuit breaker. This is the front view of 33 kV vacuum circuit breaker. These after the installation of the equipments, protection schemes of transformer were tested. Mainly three major protections of transformer that we have tested during the commissioning. In addition to this, so many testing activities are also carried out. So this is the test setup for the testing the differential protection of transformer. So this is one 33 kV winding. This is 230 kV winding. So here current is injected and simulated through auto transformer, both for in-zone and out-zone faults created and protection function were tested. This is the test setup for REF protection, and this is the test setup for testing the bus bar protection. So this is the wall bushing bus bar protection. Even though it is not part of the transformer, it is the part of the bus bar protection scheme of this 230 kV bus B. Since we have removed and replaced the bushings bushings and bus bar protection CT, it is to be integrated again with proper testing. So in-zone and out-zone faults were created in this bus bar scheme also, and again it is integrated. For making the test setup and testing arrangement in the switchyard, it was taking some 2 to 3 days for us for making connections and laying cables and other arrangements. But actual testing, it took only 1 hour. This is one major challenge we faced during this project. And one more thing, during the testing of this bus bar protection scheme, this bus B was feeding loads and which was in service. By proper operation and proper isolation of this disconnecting switches, we could be able to test this scheme without disturbing the operation of 230 kV bus B. And before commissioning of transformer, the oil of transformer was tested in ERDA for various parameters like BDV, neutralization value, dielectric dissipation factor, specific resistance, interfacial tension. So many things we have tested, and the values were found within the specific limits. And then we have gone for the, and DG also we carried out. And then we have gone for the commissioning. And transformer is provided with the fire protection with high velocity water spray system. That the system operation also was tested before the commissioning of transformer. This is the water spray which is injected over the transformer. The situation was created, and this test was carried out before the commissioning. This is the commissioning activities was going. NPCL and DAE people were together working for the commissioning of the system. This is the switchgear platform. This is the elevated platform. What we have seen is this. This is the ground condition. This is elevated platform of 1.6 meter. Over and above this 33 kV platform switchgear. This is 6.6 kV switchgear are installed. And this is the photo after the commissioning. Now we can see this indication lamps. The feeders are commissioned. All system are in working condition. In the stop area, now 230 kV is in live condition, which is taking power supply from indoor switchyard and it is sent 230 kV supply to outdoor transformer, and that transformer supply is coming back to this panel. So now it is feeding in a Fukushima compliant bay. So this is the arrangement in the transformer we have installed in that place. This is the final view after the installation before commissioning. So this is the difference. This is before we have started. This was the photo which shows the empty space where we have started and here where we have ended. So because of this project, what we achieved is the major achievements that enhanced source and power capacity to meet loads of upcoming DAE projects at IGCAR and KALPAKKAM till 2030. Then post Fukushima compliant 12 MVA 6.6 kV offsite power supply to MAPS is achieved as an auxiliary power source during BDBL flooding conditions for emergency loads, and reliable offsite power link for FBTR startup and power evacuation, and successfully implemented highly optimized and compact layout design for high voltage equipment, thus avoiding any expansion to the indoor bay. Actually, we do not have any space for constructing new indoor bay. So in the existing bay itself, we carried out this project and completed successfully. With this, I conclude. Thank you all. Thank you, IEI, for giving me these opportunities. Thank you very much. Vanakkam. Wish you all a happy Dasara and happy Diwali. Thank you. Sir, any questions, sir?
Hello.
Ah.
Sir, very informative, sir. This Mohan Raj from RCL, sir.
Thank you very much, sir.
Very informative talk. One small thing, sir. You
Yes, sir.
said about the your panels, safety interlocks you are providing now, sir. Rear door safety and all, sir.
Yes, sir. Yes, sir.
In case you are opening the rear door and other things, sir,
Yes, sir.
whether that level of safety, that is when rear door is open, whether the complete system has to be switched off, tripped, that level of safety is required, or some alarm indication will be sufficient.
No, sir. Actually, it is compulsory one because,
Okay.
1 minute, sir. I'll go to that slide. This is the panel front arrangement, sir.
Okay.
One more photo I can. Sir, this is the rear door, sir. Actually, here the cables are energized with the power supply. This particular in this panel, it is 33 kV power supply, high voltage system. Any operator by mistake, he is opening this rear cover without proper isolation. He is exposed to this high voltage, sir. It is very dangerous. So next action he will be doing either that any discharging or doing any maintenance activity only will be the next activity for him.
Okay.
So
Your point
compulsorily.
is right, sir. But whatever safety you are giving now, sir, it is through some limit switch actuation now, sir.
Yes, sir.
But because of some limit switch arrangement or something,
Yes,
there
sir.
has been some,
Yes,
you know
sir.
about this.
Actually,
But all critical loads are getting tripped. So generally, in case of any this type of major breakdown or maintenance, you
Yes,
will
sir.
generally switch off and only do that.
Yes. Correct, sir.
But this
Sir.
limit switch, whether in case there is any indication will be sufficient. That is what I wanted to ask, sir.
Yes, sir. Yes, sir. Actually, this limit switch tripping is an secondary protection device, sir. Secondary safety device. In this area, you can see one safety solenoid is there. First level safety device is this one. The second one only will be that safety limit switch. This one will not allow the operator to open the door when the breaker is in on condition. This is so your problem is getting addressed here. So person cannot open first. In case this is failure, at that time only the personal safety is the most priority. At that condition, it will trip. So definitely, it will not allow the operator to open this switch rear door at all. So that your question is correct, but that problem is addressed at the first level itself. That safety switch is the secondary one, sir.
Okay. Right, sir. Thank you. It was
Thank you,
very
sir.
useful, informative, sir.
Thank you very much, sir. Thank you, sir. Thank you very much. Thank you all.
Excellent, brother.
Thanks, Ramanathan, for giving a wonderful, lively presentation. In available space, the system was modernized and without changing the scheme, it is retrofitted and new features also added. This is a wonderful technology implemented in a short duration without new construction. That is more and more important on this. With this, I am encouraging on behalf of KLC for a token of love. We will give one small moment to Sir Ramanathan, and I am hand over. After that, vote of thanks, I am hand over to mic to Sendilar. Please join us for a small moment to hand over to Sir Ramanathan.
Thank you, sir. Vote of thanks. On behalf of IEI KALPAKKAM chapter and Tamil Nadu State Center combinedly arranged that TECHNO series of lecturers. Today, up to date, we are completed 9 lectures and another 5 we are planning. And today, speaker T. Saktivel sir, scientist for advanced 9% chromium and fertile steel swell joints for FBR system. Steam generator application. It is very useful and knowledge sharing session. And also our scientist Sri Ramanathan delivered for augmentation and replacement of power source to IGCAR. This is I am also working with him. This is still without failure and without breakdown. It is running. Thank you, Ramanathan sir. He thanks to Tamil Nadu State Center smoothly arranged 100 hours program, and also thanks to Divya madam, and once again I thanks to everyone. Thank you.